Well, thank you very much to the organizers for allowing me to make that presentation online. I wish, and I was really intending to be in person, but unfortunately, with COVID and other things, it's just not possible. So this is a joint work with Professor Riesz from University of Laguna in Spain, Edzef from Vanderbilt, and Frank Wielonski from University of Marseille. And as we have discussed already, we will call the risk potential u sigma of a measure sigma as the integral from d sigma of t over x minus t to the power s. And this, in our case, sometimes will vary from 0 to d. And most of the time will be from d minus 2, the Newton case, to d. So the external field problem with a certain weight or external field q that is lower semi-continuous on a compact non-polar set k of rd is defined as the energy of sigma plus twice the integral of q d sigma. And we are asking for a measure mu q that minimizes this weighted weighted energy, and the first inequalities are actually what is less or equal to a constant on the support and greater or equal quasi everywhere on K. Now, when Q is equal to 0, we obtain the equilibrium measure, and we will denote it with omega sub K. And when, for general Q, we will call that measure mu sub Q as weighted equilibrium measure. So this is the minimum, the optimal energy, the optimal measure for the Riesz energy on minus 1, 1, when it's 2/3, 1/3, and 0. Applications include approximation theories, statistical models in math, physics, etc. And the problem that usually is associated with these kinds of external field questions is what happens. Can we generalize things for unbounded set sigma? And the issue there is that the compactness of the set of measures then is lost, and sometimes such optimal measures simply don't exist. So suitable conditions on the set will be needed on sigma and on the potential interaction. Some classical references date back to Gauss. Frossman already mentioned. Riesz, 1938 is a fundamental paper that introduces the Riesz potentials. Relo, Cartan, the Japanese school, we already heard about Otsuka, Tsuji Mizuta, Landkopf, Helms, Ransford, and Saftotic, 1997 book. Saf told me that there is a new edition of that under construction. So with that setup, when S is d minus 2, that's the Newtonian case, then we can recover the measure by taking Laplacian of the equilibrium, not of the equilibrium, but of the potential. And when S is between minus 2 and d, that corresponds to fractional Laplacian, so negative Laplace to alpha over 2. And this is a linear non-local operator. It's defined in the following way. And in distribution sense, this does satisfy the point mass equality that is associated with the Newtonian case. So some of the good, this is our good range, let's call it this way. Many things happen when S is greater or equal to D minus 2 and less than D. So we have a principle of maximum on the support. We have a domination principle. There is also the notion of balayage that extends to that set, and that's by Riesz approach that is described so well in Lankov's chapter 4, section 5, for those of you that want to revisit. And in addition, we will see there is also the Vall theorem that holds in that range. So this is why many of the approaches or the studies are focused on that range of the parameter for Riesz. So there is unique, for balayage, there is unique mu hat such that the support is on F. So we're balayaging mu is supported outside F, and F is a subset. So we're balayaging it, the measure mu, onto F. And we will assume that mu is with finite energy. So then the balayage measure is defined by the potential coinciding with the potential of mu quasi everywhere on F, and being less or equal everywhere on RD. And that can be derived from the domination principle. Now, there is one trick. The norm does not need to be, the same. It can decrease. So potentials are not superharmonic, but alpha superharmonic in that particular region. And this is, the definition. And in the other range from 0 to D minus 2, many of the good, they are potentials are superharmonic, but many of the good properties fail. So that's why most of our work is restricted to D minus 2 to D case for Riesz kernel. Now, irregular points and thin sets, just a brief overview. A point is called irregular, that's the Newtonian case, if for any continuous function there exists a solution of the Dirichlet problem without boundary data. And that solution is continuous. So an example of 0 being irregular is if we consider the unit ball or unit disk, and then F is 0 on the circumference and F0 is not 0. Another example is the Lebesgue spine. And the thinness criteria, that's the Wiener criteria, is that this series, sum k from 1 to infinity, 2 to the ks capacitive, the intersection of D with small balls of radius 2 to the negative k surrounding x. If this series is less than infinity, then D is called to be thin at that point. And X is irregular point for a domain D if and only if the complement is thin at X. And when sigma is a positive measure and X0 belongs to RD, there is set E thin at X0 such that the limit is that there is that equality that holds. Okay, so potentials are continuous in the fine topology. So the existence of the minimizing measure mu q on unbounded sets is there is a nice and simple condition when Q of X approaches infinity. Then if you recall, we had two terms in our weighted energy. One of them was the energy of a measure, and the other was the integral of the external field versus the measure. And when Q approaches infinity, that simply restricts the minimizing measures to compact subsets. And therefore, we will be able to apply Banach-Steinhaus theorem and get minimizing measure. So the compactness argument actually does work. But when the limit does not exist, maybe is some finite number, when it's not blowing up, so to say, as X approaches infinity, then what we need is that the point at infinity be not thin, and some sufficient conditions for the existence of mu q that we derive in this work is that Q of X for large X in that unbounded set sigma, Q of X is less or equal to Q infinity minus 1 over X to the power S. So this is one sufficient condition. Sufficient condition for non-existence is if there is C that is smaller than 1, so that Q of X is bigger than that difference Q infinity minus C over mod X to the power S. And the necessary condition for the support of mu Q to be unbounded is that Q infinity is a finite number, and the limit is, absolute value X to the power S, Q of X minus Q infinity equals -1. Let me know if there are any issues. Zoom is telling me that my internet connection is unstable. I hope it stays on point. So one easy example is let sigma be unbounded and 0 does not belong to sigma. Then we can consider an attractive external field, place an attractor of charge C at the origin. And then that external field is Q of X is -C over absolute value X or norm X to the power S. And the limit of QX is 0. And the theorem tells us that when C is greater or equal to 1, the minimizing measure mu Q exists. When C is strictly greater than 1, the minimizing measure has bounded support, so the attraction is strong enough. Now, when C is strictly less than 1, the minimizing measure does not exist. So these are the conclusions that we can derive. Now, let me pause before I move forward and say how external field problems have been used to, derive various properties for optimal configurations. Usually, optimal configurations are, minimizing some energy, and in that particular range, for example, for the Riesz energy point, when the range is from on SD, when the range is from -2 to D, Etzaf and I were able to establish the separation property utilizing an external field problem. And the way that we worked it out is we fixed one of the, say, big N points and considered the external field that exerts on the rest of the points. then what we did was these other guys, discrete external field minimizers, and they're contained in the so-called continuous minimal energy point, and therefore prove that the continuous energy point has a small neighborhood surrounding that fixed charge where there is support. And that actually led to separation theorem. So the connection between continuous energy problems and discrete energy problems is really very intricate and quite well distinguished. Now, one of the things that are important is that for this particular range of the parameter d minus 2 to d, the discrete energy, or with external field, the discrete energy points with certain external fields are actually contained in the extremal support for the continuous problem. So this is important property, and again, that holds for this range. So how do we prove that particular statement here about the existence of the equilibrium measure? With Kelvin transform, we can take everything, lift it up into d plus 1, and fix, say, y to be 0, all first d coordinate 0, and then 1, the d plus first coordinate. So it's North Pole, and then with this a stereographic projection, we're able to lift RD onto SD in RD plus 1, where the point at infinity goes off to the North Pole. And there is also that was introduced by Kelvin, the Kelvin transforms function, and it's linear, involutive, preserves positivity, harmonicity, and subharmonicity. And I will define the Kelvin transform for measures here. So d mu star is 2 to negative s over 2, t star minus y, norm to the power s d mu t. And then, with that, the value at that North Pole of mu star multiplied by 2 to the power s over 2 is actually 1. When s is 0, the total mass is preserved as the log case, and one gets an equivalent minimization problem with external field. And when s is bigger than 0, the normalization is changed, and the Frossman inequalities also. So for sigma unbounded, we approximate t sigma n minus small. So we exclude a large ball centered at the origin from sigma. So it's really the p outside. And we obtain a sequence of minimizing measures mu n on that set. And they have compact support and masses are uniformly bounded. So we're able to find a weak star limit for, and that weak star limit we will denote with mu star. And we directly check that the Frossman conditions are, inequalities are satisfied. So a more elaborate example, this is when we have a single attractor, but this time we will take it above RD. Now a conductor, or our sigma variable set, is going to be the whole of RD. So imagine that you have the plane and you have an attractor, negative charge, atop that plane at some height of yd plus 1. We can take it to origin at rd. So we get a non-convex external field of this form, gamma, divided by norm x squared plus yd plus 1 squared, all that to the power s over 2. So then mu q exists, provided gamma is strictly less than -1. That's the first assumption that I have on the slide. And the support is a closed ball by a rotational symmetry and the uniqueness. And the R0 is given as that unique solution of this equation. And below you can see the density as function of R for D equals 3, S is 2, and gamma is -5. And depending on the height is 1 or 2. Okay, so this is one example. So how do we compute mu q? Let's back up a little bit. Now, one of the things that are used, and here we will restrict ourselves to S between D minus 2 and D, but we can balayage the measure, the point mass measure delta sub y with certain charge gamma, right? We can balayage it onto RD. How does the balayage work? Well, the balayage works in the following way. There is balayage. You take the spherical, you take the stereographical projection, and RD goes into SD with YD plus 1 being the North Pole. So we do it in that special way with, that Y being the center of the sphere with respect to which we evaluate the stereographical projection. Now, the radius is chosen in a special way that, say, the origin of RD is preserved, so that's a fixed point. So then one can define what kind of, radius one wants. And the resulting sphere, the equilibrium measure of that sphere is S on SD, is the, normalized. We can normalize it the way we want, but it's uniformly distributed, so it's unique. And then when we take the Kelvin transform of that unit measure on the sphere onto the, RD, then that is actually the balayage measure. So let me just restate briefly the procedure. You take stereographical projection, find the equilibrium measure, take the Kelvin transform of that equilibrium measure back, and that's how you get the balayage measure. So one can write down a negative measure with, mass actually does preserve the mass when you balayage onto an unbounded set. So with the same mass, gamma and negative measure onto RD. So that external field can be written as a potential on RD. And then what one does is the signed equilibrium feature and the iterated balayage algorithm. So we can write down the signed equilibrium as something, a signed measure of total mass 1. We want to keep always the total mass to be 1, because in the limit, that signed equilibrium will approach the equilibrium measure, positive equilibrium measure, which is probability measure. So by keeping the mass 1 is one nice way of actually maintaining that convergence. And what we want is that the weighted equilibrium is constant on all of sigma. Well, sigma is RD in our case. So then, we compute the balayage gamma delta sub y, and we can write down the signed equilibrium underneath here is negative gamma that balayage plus 1 plus, now maybe I should have said, we compute the balayage on RD. Then that balayage can be computed again onto large ball. So this is like taking a balayage into steps, all right? And that balayage onto that large ball, we offset with the equilibrium measure onto that ball so that the total mass becomes 1. And then the equilibrium support is derived by finding that particular value, the largest root of HR, which is HR is the density on the boundary. So the largest value of R0 such that HR is 0. So that's how we determine the equilibrium measure. So it's assigned equilibrium, but for that fixed R0. And the iterated balayage algorithm actually goes down to with sequence of decreasing values of R that have a limit R0. That's how one can utilize that. And this is the equilibrium measure statement. That's what it looks like. It's quite elaborate and detailed. I will not focus too much. So the potential of sign measure, this same result can be extended to any potentials that are supported outside RD, okay? And then what we can do, that point mass result that we had, it derives the balayage of nu can be derived by point mass balayages and the superposition principle. So one can write down that balayage for nu onto RD utilizing the point mass balayage and then integrating all the density or the measure nu. So in some sense, you take a balayage delta sub y and then you integrate it with respect to nu, d nu y. And that's how you determine the balayage of nu onto RD. So if sufficient conditions in the admissible case is when gamma, that charge, is strictly smaller than -1. So if this is the case, then we have a compact, support, and whenever the u of RD plus 1 is less or equal to -1, there exists a unique equilibrium measure. And the weakly admissible case is when it's exactly -1. Then this is the condition that guarantees that the support is compact. Again, this is the range for S from D-2 to D. So further, one can also define discrete settings where we have finitely many, or possibly with more general measures, infinitely many points. And again, a similar condition gets stated. So there is also, one can have, well, that was assigned measure, the general result in the particular case where you have attractor repellent pair, one can get various direct computations. Now, about that fact that the support of mu q is a subset of the support of the positive part of the signed equilibrium, it dates back to with Arno, we utilized it to prove things for the logarithmic potential back in '99, where we introduced also the iterated balayage. And it is based on the domination principle and the Vall-Poussin theorem that is listed here. Now, it's listed for the Newtonian case. At the time, we based it on the book of Ed and Willy Totik. They have that theorem stated there. Now, we would like to extend this to the Riesz potential in that particular case. So let me see, I have about I'd say 5 minutes, so I'll go briefly over the proof of that, that the support. We have the Vall-Poussin theorem introduced, stated by considering the signed equilibrium at a q, let it be at a q plus minus at a q minus, and the total mass equality, it's like that. Then we have equality on the support of mu q, and we have inequality everywhere. Now, this actually tells us that the second inequality holds everywhere. Now, for that, for Riesz S potentials, this requires the alpha superharmonicity property, and one needs C minus FQ to be non-negative constant. Then one can extend it indeed, because eta Q plus is supported on K, so this holds quasi everywhere, and therefore almost everywhere on K, mu Q, I'm sorry, eta Q plus almost everywhere, because eta Q has a finite energy. So this can be extended everywhere, and by the Vall-Poussin, then we have that quality. Okay, so let me go. I'll just review quickly the proof of that, I would say, most fundamental tool that we used. And in the Newtonian case, it's kind of local. There, what we need is that u nu is less or equal to u mu plus c in some domain, and then on the set of omega, that domain, where we have equality, mu minus nu is a negative measure. Okay, so we'll use the average LR, that is 0 radius R, and sigma is actually the unit uniform measure on the sphere. R go to 0, we end up with the value being u mu of x0, and it's discrete, absolutely continuous function, and this is what the derivative looks like. Then pick an x0 in that set, and L nu is less or equal to L mu plus C at R, for R small enough, and that allows us to get to this inequality, and we can derive the result from covering for the equilibrium measure is supported everywhere. And if you take the zero measure, then we have equality on any open subsets of B, because the equilibrium potential is constant there. And in particular, that is such an inequality. So this, being a negative measure, actually does fail. Okay, because it is strictly positive measure on all of the ball. So on any sub domain omega of the ball. So a global version is required for the Riesz case. So the inequality, and I have indicated the potential dependence on S. This is for D minus 2 to D, that range. Require that everywhere in RD, and then mu minus nu restricted to the equality set is a negative measure. And unfortunately, I think I ran out of time, but these are the two slides of that proof. Here, there are any